A person is running at some speed. Let's count the number of times the person hits the boundaries in 1 minute. 1, 2, 3, 4, 5, 6, 7, 8. Now, what happens if he is running at a speed double of this speed? Now let's count the number of times he hits the boundaries in the same time. That is in 1 minute only. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So when he was running at a speed which was double the initial speed, he touched the boundaries double number of times. Now we give him a condition. We say that he can touch the boundaries 8 times only when he is running at double the speed. How is that possible? Since now he is running at double the initial speed, so if he has to touch the boundaries 8 times only, that will only be possible if he covers a greater distance. And how great the distance or how big the distance should it be? Since now he is running at double the speed, so now he should cover double the original distance. So now he has double the distance to cover in the same time. That is in 1 minute only. Let's count the number of times he hits the boundaries. 1, 2, 3, 4, 5, 6, 7, 8. So if he is running at double the speed, in order to touch the boundaries the same number of times, that is the initial number of times, he has to cover double the original distance. So let's compare. So now the person is running at double the speed. So in order to cover the distance, that is in order to touch the boundaries the same number of times, if he is running at double the speed, he has to cover a greater distance. So here you see they touch the boundaries at the same time. So when the person was running at double the speed, in order to touch the boundaries the same number of times, he had to cover double the distance. So we see that the distance covered is directly proportional to speed. So greater the speed, greater the distance covered, lesser the speed, lesser is the distance covered, given that the number of hits per unit time remains constant. Something like this was used by a scientist named Charles. He performed an experiment known as Charles' experiment in 1787. Let's see what he performed. He took this apparatus. This has a beaker which has water inside this. There's a thermometer. There's a scale and a capillary. A small capillary is a very small fine tube. So a capillary is attached to this scale using rubber bands. Such an apparatus in which water is present to provide heat to the other devices present inside it is known as water bath. What is the purpose of water bath? Well, when we have a system like this, the purpose of water bath is that it provides a uniform temperature throughout. Since it gains a temperature, so the temperature throughout this water, that is the temperature of the thermometer, temperature of the capillary and the scale, so the temperature throughout remains the same. So he used this device. The pressure for this experiment was maintained constant. How was this done? We know pressure at the same height remains the same. So this capillary tube, which he had used during the experiment, is at the same height throughout the experiment. Since it is tied by rubber bands, it is maintained at the same height throughout the experiment. The height of the capillary is not changed, so throughout it experiences a constant pressure. Now, if you'll observe, there is gas enclosed in the capillary. This area shows that there is a gas which is trapped in the capillary. The remaining volume is the water which is filled in the capillary. So there is gas enclosed in this part of the capillary. Now he started heating this water. As he heated, the temperature started to increase and the volume of the gas in this capillary started to increase. So you observe when he closed the burner, he switched it off, the temperature decreases and the volume of the gas also decreases. So what did he observe here? As he was increasing the temperature, as he was heating the water bath, the volume of the gas trapped in the capillary, that also started to increase. As the volume of the gas started to increase, the water in the capillary tube started to fall. That is how the volume of gas in the capillary started to increase. When he switched off the Bunsen burner, he switched off the flame, so the temperature started to decrease. As the temperature decreased, the level of water increased. This was because the volume of gas enclosed started to decrease. As the volume in the capillary started to decrease, the water level in the capillary started to increase. So from this experiment, Charles observed as the temperature of the water bath was increased at constant pressure. Since he was observing the gas which was trapped in the capillary tube was maintained at the same height throughout the experiment. So he maintained constant pressure throughout the experiment. He observed as the temperature of the water bath was increased, the volume of the gas enclosed in the capillary tube increased. And if the temperature was decreased, the volume of the gas enclosed decreased. So he observed that when he increased the temperature, the volume of gas enclosed increased. When he decreased the temperature, the volume of the gas enclosed decreased. So based on this experiment, he gave his law, which is known as Charles' law, according to which for a particular gas, if the pressure is kept constant, the volume is directly proportional to temperature. This means greater the temperature, greater is the volume of the gas, lesser the temperature, lesser is the volume of the gas. So this law is known as Charles' law. So this is, as we had seen before, for the person running. So we had observed greater is the speed of the person, greater is the distance covered by the person, provided the number of hits per unit time remains constant. So for Charles' experiment or for Charles' law, what did we observe? The distance covered is the volume of the gas, the speed is the temperature, and number of hits per unit time remaining constant, which is the pressure. So for Charles' law, as the pressure remains constant, the volume of the gas is directly proportional to its temperature. So let's revisit the Charles' law. It states that for a particular gas at a constant pressure, the volume of a gas is directly proportional to temperature. This means to remove the proportionality sign, we introduce a constant. So we get that the volume of a gas is equal to constant into temperature. Now we bring the temperature on this side. We get that the volume of a gas divided by the temperature of the gas is a constant. So according to Charles' law, for a particular gas, volume by temperature for a particular gas is constant provided the pressure is constant. So the value on the Celsius scale, we already know, can be converted into the Kelvin scale by adding 273 to it. So in Charles' law, whenever we talk of temperature, we always use the Kelvin value. This Kelvin value was given by Lord Kelvin, and this scale is known as the absolute scale. The Kelvin scale is also known as the absolute scale of temperature. So whenever we talk of temperature in the Charles' law, we always use the Kelvin value. Now let's perform an experiment to prove the Charles' law. So a gas is enclosed in a container. The pressure is kept constant, which you'll observe here. Now we'll increase the temperature of the gas. So observe what happens. You can see through the thermometer that it is heated, so the temperature rises. As the temperature increases, the volume which is enclosed increases, or vice versa. As the volume increases, the temperature increases. So you observe these values and you see that V by T. So according to Charles' law, volume by temperature is a constant. So these values, that is, we know that the temperature is always taken in Kelvin. So all these readings are converted to Kelvin, and volume by temperature in Kelvin, that value, that is V by T, temperature in Kelvin, is always a constant value, as you can see. So from this experiment we see that V by T is always a constant value, provided the pressure is kept constant. So according to Charles' law, as the temperature decreases, volume decreases. How far can this volume decrease? We know a temperature 0 Kelvin was given by Lord Kelvin, which he called absolute zero. At this temperature, all molecular motions cease. That is, the speed of the particles becomes zero, and at this temperature, the volume of the gas is reduced to zero. So this is the temperature at which the speed of the particles becomes zero and the volume of gas is also reduced to zero. So if a graph is plotted for the Charles' law, we see that volume is directly proportional to temperature. So we get a straight line. That is, as temperature increases, volume increases. Now if this value we extend backwards, we see that it meets the graph at minus 273 degrees Celsius. This is 0 Kelvin. That is the absolute zero temperature at which the volume of all gases becomes zero. So at this temperature, we see from the graph that as the temperature is reduced to 0 Kelvin, the volume of the gas becomes zero. So this is the graph for Charles' law, which is also known as an isobar. Iso means same and bar is used for pressure. So in this graph, since in Charles' law the pressure remains constant, so this shows that for the same pressure, this is the graph that is obtained for the values of volume of a gas for a particular gas versus its temperature. The volume of a gas increases with the increase in temperature. Is it true or false? So from Charles' law, we know that the volume is directly proportional to temperature. As temperature increases, volume increases. As temperature decreases, volume decreases, provided the pressure is constant. So we have the volume of a gas increases with the increase of temperature. So this is true. We see that as the temperature increases, the volume increases. So based on the experiment that Charles had performed and the data collected, he gave his law. His law states that the volume of a given mass of air. So notice that the law is valid for a particular gas. The volume is directly proportional to its absolute temperature. We know whenever we are talking of Charles' law, the temperature which is referred to is always the Kelvin or the absolute temperature. So the volume is directly proportional to temperature provided its pressure remains constant. So we know that the volume is directly proportional to temperature provided the pressure remains constant. So this is the law, this is the Charles' law for a particular gas. So let's revisit the Charles' law. It states that V by T is constant. Let's denote this constant by K at a constant pressure. Now say this is the initial volume of a gas. This is the initial temperature of a gas. So V1 by T1 is some constant K. If this is the final volume of the gas, volume 2, and this is the final temperature of the gas, T2, so V2 by T2 is also constant. So if we combine these two, we get that V1 by T1 is equal to V2 by T2, which is the same constant K. So we get that V1 by T1 is equal to V2 by T2. This means for a particular gas at a constant pressure, the volume, the initial volume of a gas divided by its initial temperature is equal to the final volume of a gas divided by its final temperature. Let's try to study the Charles' law based on the kinetic theory. So we see that there is a direct relationship between the volume and temperature of a gas. So as the temperature increases, volume increases. As temperature decreases, volume decreases. What is happening here? So as you see, the pressure remains constant, which you can observe from this pressure gauge. So the pressure remains constant. As the temperature increases, the kinetic energy of the particles increases. As the kinetic energy of the particles increases, the speed of the particles increases. As the speed increases, they strike the walls of the container more. Since the pressure has to be maintained constant, so if they strike the walls of the container, they increase the volume of the container. So with the increase in temperature, the volume increases. Similarly, we get the vice versa case. If we decrease the temperature, the kinetic energy decreases, the speed of the particles decreases. This means the number of strikes or the number of hits per unit time has to decrease. Since pressure is constant, this is possible only for a lower volume or a lesser volume. So let's revisit. As temperature increases, the kinetic energy of the particles increases. As the kinetic energy increases, the speed of the particles increase. As the speed increases, the number of hits per unit time also increases. But in Charles' law, the pressure has to be kept constant. This means that pressure is constant. So this is possible only if the volume is increased. So the increase in number of hits increases the volume for a constant pressure. Similarly, we get the vice versa case. If the temperature is decreased, the kinetic energy decreases, the speed decreases. As the speed decreases, the number of hits per unit time decrease. Since pressure has to be kept constant, so the volume decreases. Only when the volume decreases, the number of hits will decrease for a constant pressure. So for Charles' law, as the temperature decreases, the volume decreases. Now let's try to solve a question. To what temperature must a gas at 300 Kelvin be cooled in order to reduce its volume to 1/3 its original volume, the pressure remaining constant? Since we see that the pressure remains constant, this means this law or this condition is valid for Charles' law. So let's use Charles' law here. It states that volume is directly proportional to temperature, or V1 by T1 is equal to V2 by T2. Let's write the data that we are given. So we are given that the initial temperature of the gas is 300 Kelvin. Keep in mind, whenever we are doing Charles' law, we have to use the absolute or the Kelvin values. So in this, we are already given the temperature in Kelvin, so we do not have to convert it. If the temperature was given in degrees Celsius, we always have to convert it to the Kelvin value. Now, we have to find the final temperature. Let's take the initial volume to be V, since we are not given any volume, and it says that the volume is reduced to 1/3. This means the final volume is 1/3 the original volume. Now let's apply Charles' law to this. So we have V1 by T1 is equal to V2 by T2. So we can cancel this. V1 is V, so we can substitute this by V, as we have taken V1 is equal to V. So we can cancel this V on both the sides. What do we get? And we get T2 is equal to 300 divided by 3, which is equal to 100 Kelvin. So to what temperature should it be cooled? It should be cooled to 100 Kelvin. What do you observe here? We know by Charles' law that the volume is directly proportional to temperature. So as the final volume is reduced, this was the initial volume, the final volume is reduced, so we'd see that the final temperature is also reduced. Since the initial temperature was 300 Kelvin, the final temperature is 100 Kelvin. Here there is a plastic bag filled with air. So now, if this plastic bag is kept in a freezer, it's taken out after 20 minutes. It's observed that the plastic bag has deflated. So as the temperature decreases, the volume of the gas decreases. And if it is heated on top of a flame, so as the temperature increases, the volume of gas increases. So you observe that the plastic bag re-inflates. So this is the Charles' law, which states that the volume of a gas is directly proportional to its temperature at a constant pressure.